Hi, this is Pankaj Kumar. In this video, I will cover the 1D meshing and analysis. So, the question asked is when we use 1D element. So, when one dimension is larger in comparison to the other two, we use 1D elements. So, the element shape, as you can see here, is a line, and the additional data that is needed from the user is the remaining two dimension or the cross sectional area. The element types in the 1D elements are rod, bar, beam, pipe, axis metric cell, etc. So the practical application of 1D analysis or the 1D elements are long shaft, beam, pin joint, connection elements. So the different type of elements are having their different behavior and the properties. Like the rod element can sustain only tension and compression loading and torque for some software. So if there is a need of the compression and tension loading, so the rod element can be used. Like the thrust analysis, there is a tension compression member, so we will use the rod element. For the bar element, all the 6 degree of freedom, like translational about x, translational about y, translation about z, and rotation about these three axes are available, but the bar element is applicable for only symmetric cross sectional. So for the shaft subjected to multi-axial loading, like bolted, welded joints, connection elements, the bar element is used. If the available cross section is unsymmetric, so we have to use the beam element, which is same as bar but also support the unsymmetric sections. There is a different other type of pipe element which is also same as beam, but it has a non-zero diameter. So if you are doing any analysis of the pipe that is of any component that is having the non-zero diameter, internal diameter, you have to use the pipe. So pipe is also same as the bar element, beam element, but it has non-zero internal diameter. The pipe element is used for piping systems and structural analysis. There is a axisymmetric shell element which is used for the thin shell pressure vessel, cylindrical, conical objects, etc. This one element support the translation about x and z, and rotation about the y, where the z is the axis of the symmetry and x is the radial direction. For the objects symmetric about the axis of rotation and subjected to axisymmetric boundary condition, the axisymmetric solid is used. So now we will start with the analysis. The first exercise we have, in which there is a rod that is subjected to the tensile force. The diameter of the rod is 50 mm and is 500 mm long. This one is and this rod is constrained at the one point, and a load of 1 into 10 to the power 5 Newton is applied on the other side. The material for this rod is steel, in which the elasticity modulus is 2.1 into 10 to the power 5 Newton per mm square, and the Poisson ratio is 0.30. So first we solve this problem by analytical solution, in which the stress that comes out is 50.95 Newton per mm square, and the displacement that comes is 0.12 mm. So this one is the analytical solution, and we will do the same analysis with the same boundary condition in the HyperWorks, and we will compare and validate the results. So for the most linear static 1D analysis, this one formula is used, where the M stand for the material collector, H for hyperbeam, P for property collector, C for component collector, L for load collector, and the last L for load step. These collectors are used to collect the information regarding what they are. Like the material collector collects the material properties. In the material collector, we can define different type of materials, which may be used in for the component or the different elements. Property of the elements are collected by these property collector. The components informations are collected by the component collector, and the load regarding uh, the loads are collected by the load collector. So now we will start to HyperWorks. So this one is my HyperWorks graphical user interface. uh, so first of all, I will create the geometry in this in the HyperWorks. So first I have to create according to this one formula, the material collector. As you can see here, my material is steel. So I will first define my material. So to define the material, click on the material collector icon here. This is, and type the material name as steel. The material type will be isotropic. This is because in anisotropic the property of the material is changes with the direction. For the fluid related problem, you have to select it as fluid, and I will select isotropic. My card image will be mat 1, because the card image mat 1 supports the structural properties, and mat 4 for the thermal properties. So as this one is my structural analysis, so I will select it as a mat 1. So I will make it card edit to edit all the information, or provide the material properties. By default, in the HyperWorks, the property available is of the mild steel. Here the elasticity modulus and the Poisson ratio is the same, as here I have considered this one as the material defined in this one exercise. So I will make it return from this menu. Then the second step is to create the hyperbeam or the cross section. The hyperbeam is used to create the area or provide the other two dimension. As we have explained that in the 1D element we have to provide the other two dimensions. So as you can see here, the external diameter is 50. So now I will go to 1D panel and click on hyperbeam. So as I have to create the standard section, so I will move my toggle button to standard section, and select the standard section type to a solid circle. And now to create, I will click on the create. So now the panel is loaded for this for the hyperbeam, and here I have to provide the radius. As the external diameter is 50, the radius will be 25. So I will return by click on exit to the HyperWorks. So now as you can see here, uh, in the model browser, the beam section is created. So now after this one, the next step is to create the property. So to create the property, click on a property collector. Property name will be prop. The type is 1D because as you can see here, this one dimension is larger as compared to the other two dimensions. So the type will be 1D. Card image will be rod because my component is loaded by the tensile force and there is no other bending or other axial forces are there. The material is steel and the beam section is circle section 1. So I will click on create. So now the property is created. So after the property, the next step is to create the component collector. So now to create the component collector, click on component icon and the component name will be rod. The card image for this, as there is no card image is needed for the OptiStruct profile, so I will make it no card image, and the property is already taken by the material collector, that is the property, and then I will make it create edit. So now the component collector is created. So then I have to create the component. So to create this one component, I will create a node. So to create the node, go to geometry menu page and click on nodes. So I will create a node at the origin of this system coordinate. So the system coordinate is 0. It means that I am using the global coordinate system, and the x, y and z, all these values will be remain 0. So now here my node is created. So after this one I will create the other one node at a distance of 500 mm from this one node along the x direction. So 500 and make it create. So now these two nodes are created. So first I will solve this one problem with with single element, and then I will solve the same problem with more than 5 or 6 number of element, and I will compare how the number of element affect the accuracy of the results. So now after creating this the two nodes, I will create the element. So to create the element, go to 1D panel and select rods, then select the nodes. The property will remain the prop, and the element type will be C rod. So as you can see here, this element is created as a C weld, but I want to my element type is C rod, so I will update this one element and see how now this the element is now updated to the C rod element. So now I will see whether the properties are properly assigned or not. So I will assign this one property, assign and proceed. Yeah, here you can see that the property is assigned to the element. So now after working on the component collector, I will move to load collector. Here I have to create the two load collector, one for the constraint and the other for the loading. So to create the load collector, click on load collectors. The load collector name for the constraint will be SPC, means single point constraint, and my card image will be remain the no card image. I will create, and then I will create the other one as a load and click on create. So now the two load collectors are created. So now as said that the collectors are used to collect all the information. So when I apply the constraint at this one node, so this one constraint related information should be collected by the uh, SPC load collector, which I have defined to collect the constraint related problem. So I have to make it current, so that this information regarding the collector will be collected by the SPC. Otherwise, if I will assign or the constraint, then this information will be collected by the load. So to make the SPC as current, so I will make it as current. So now as you can see that the SPC collector becomes the bolt. It means that now when I will create the constraint, the information will be collected in the SPC collector. So I will click on this, select this node, and here for the degree of freedom, I will fix all 6 degree of freedom. So I advise you to uh, check by changing the degree of freedom, so that you can get an idea how the degree of freedom is uh, important, or the degree of freedom affect the results. So I'll click on create. As you can see here, the constraint is created. So to differentiate the different type of loading, I will change the color. So here you can see this one is red, and now I have to create the load. So to create the load, I will click on force and then click on this one node, and the magnitude as assigned uh, as defined on the other node is 1 into 10 to the power 5 Newton. So I will make it magnitude or the x component force as 1 into 10 as 1 e 5. So now the x component of the force is 1 into 10 to the power 5 Newton in the direction of x. The magnitude I will make it as 10, and I will create. So now the force is created, but the magnitudes are very large. So I will decrease the magnitude percentage. So here my force is applied. So as I have explained that we have to make the load collector current, for which we are creating the load. As you can see here, I have created the force, but this information is collected in the SPC. So I have to organize these loadings. So I will click on organize in tool panel and uh, select the loads, and this one is my load, and my destination component will be load. So I'll make this one as move. So now my loadings are created and the load collector are created. So now I have to create the load step. Load step is used to provide the information regarding the analysis, like what type of analysis I want. Here the type will be linear static, and which loading or which constraint I am considering. So the name will be 1D rod problem, and the SPC, I will click on SPC, and for the load I will select the load. So here the load collector IDs are assigned, and then I will make on create, and as you can see here the load step is created. Solve this one problem, click on OptiStruct from the analysis panel, and here the export option to all, run option to analysis, and memory option will remain the default. So I'll click on OptiStruct. So I'll click on yes, and the solver is started. So now the process is completed. So then I will click on close. So to view the result, so I will split this one screen into two, and when I click on this one, the whole panels are changed, and the hyper mesh menu is changed to the hyperview. So I will make it load model, and then I will open the file. HM24. So I will load the result, and so I will search for H3D file. So when I click on apply, so to open the hyperview, I will split this one graphical window into two by clicking on page window layout, and then I will move this one to 2, and here this one is my input file, and here this one these results are loaded. So when I click on this one, the panels are changed. So I will click on apply. Yes. So now to view the result, I will click on contour, and here the result type is displacement. This one is my magnitude, and I will click on apply. So as you can see here, my displacement, the maximum displacement is 1.21 E01 in scientific nomenclature. So when I will compare this one result with the analytical, as you can see here, the displacement is 0.12 mm, and as you can see here, it is 1.213 mm. So it is the both two results are approximately equal. So now I will go see the element stresses, zero axial stresses, and my average method to simple, and then click on apply. So as you can see here, the maximum stress is 5.09, as you can see here, and the stress by the analytical solution is 50.95. So both the two results are also same or approximately equal. So by this we can say that our FEA result is uh, validated by the analytical method. So it is always advisable to compare your result with the analytical or practical behavior of your body, because the results in the FEM mainly depends upon the applied boundary conditions, and the results may vary. So don't go behind the colors or blindly behave on the FEM or FEA results. So first you have to validate your result to whether the proper boundary conditions and loadings are applied. So now as you can see, when I will change the boundary condition like the uh, this one constraints, I will just make the degree of freedom 1 active and update this one SPC. So I updated, and now I will move to the analysis, and the file name I will change, and then I click on OptiStruct. So now the solver is started to run, and now the results. So now I will split this one in 4, and then I will open, and then click on apply. So now I will see for the stresses. So as when I compare this one, there is no effect of this one, because the rod element only uh, support the compression and tension. So if you are using the rod element, then you have to constrain the nodes in the loading directions. So now I will see how what will happen if I will uh, change my force direction from x to y, as rod element are used just for the compression and tension. So I will update my force, and now when I updated the vectors and the magnitude, my force is changed. So now I will solve these one problems. So now I will so now I'll update this one, and now I will see now what is my stresses. So here as you can see that the stresses are 0, because this doesn't support the yes. So now I will move my result type to displacement and see what about the displacement. As you can see that my displacement is increased, and I will here the displacement is, so I will move this one to, so